Welcome to the debate. We are seeing just an incredible acceleration in technology right now. I mean, the explosion in AI innovation, it's generating new materials, patents, prototypes just constantly, it feels like. But underneath all this software excitement, there's a really fundamental constraint: hardware. The demand for compute power is, frankly, far outstripping our capacity to produce the silicon, making chip scarcity, the primary bottleneck for AI's growth right now. And this urgency, well, that brings us to our central question today. Is the powerful software and ecosystem lock-in, the famous example being Nvidia's CUDA platform, is that strong enough to keep general-purpose GPUs dominant, maybe even irreplaceable for the next, say, 5 to 10 years? Or will the sheer economic pressure and, frankly, the superior efficiency of highly specialized chips like ASICs and TPUs inevitably force a disruption? I'm going to argue that the ecosystem's deep roots ensure GPU dominance, at least in the near term.
Okay, yeah, I definitely see that argument. But I'm coming at this from a slightly different angle. While, look, the strength of the CUDA ecosystem is undeniable, it really is the gold standard today, I'm arguing that the sheer unrelenting need for extreme efficiency, driven by exactly that hardware bottleneck you just laid out, well, it means specialized chips will eventually force the market to get over that software hurdle. The future path for AI, it seems to me, is defined by optimization at massive scale. And that's just a game where general-purpose hardware starts to lag behind dedicated solutions.
My position, it's really grounded in the reality that NVIDIA's strength isn't purely about raw hardware specs. It's about the platform, the ecosystem maturity. CUDA, their parallel programming framework, isn't just, a driver. It's this huge software layer built up over a decade. Compilers, libraries, debugging tools, massive community support. It has become, without question, the industry standard for running AI models. And this creates, powerful developer lock-in. Think of it less like picking a new phone and maybe more like trying to migrate a giant company off some decades-old, bespoke legacy system. The upfront hardware costs might be high, sure, but the pain, the time, the risk involved in ripping out and replacing millions of lines of highly optimized CUDA code, C++ code, it's often just prohibitive. And the GPU's broad utility is key here too, right? It supports gaming, academic research, and crucially, basically every type of AI development, from massive models like ChatGPT down to smaller, custom tools. That flexibility, I think, guarantees its central role. So, in my view, disruption stays mostly in R&D until someone offers a really credible, established developer alternative.
That analogy about migrating off a legacy system is interesting because, yes, it speaks to pain. But I think it fundamentally miscalculates the incentive here. We're not talking about just, marginal efficiency gains. We are discussing the core infrastructure for companies projected to be trillion-dollar titans within a few years. When the cost of electricity and the scarcity of chip supply become the main choke points holding back growth, that developer pain point you mentioned, it shifts from being an inconvenience to being a necessary cost of doing business, something you have to tackle. And, look, the market shift is already underway. We should probably define what we mean by specialized chips. Things like ASICs, application-specific integrated circuits, and TPUs, Google's tensor processing units. These are essentially purpose-built hardware. They're designed to do one job, which is the heavy mathematical lifting required for AI, and do it far, far more efficiently than a general-purpose chip that also has to worry about rendering graphics or running physics simulations for games. I mean, the history of computing already showed a shift from CPUs to parallel processing with GPUs, right? So the next logical, and I'd argue necessary shift, is towards this kind of specialized, hyper-efficient architecture to handle the just unprecedented scale AI requires.
Okay, I appreciate you making that distinction between general and specific hardware, but I want to push back a bit on that idea of inevitability. We're talking about the weight of inertia here. Competitors, they frequently present chips that benchmark better on paper, and yes, TPUs certainly do for specific, narrow workloads. But without that established CUDA maturity, they face a genuinely staggering developer adoption problem. I mean, imagine you're debugging a complex proprietary language model, hundreds of billions of parameters. You need a stable, proven, widely supported platform. That kind of trust, it can't just be built overnight. And that trust is a huge part of what Nvidia sells.
I'm sorry, but I just don't buy that the developer friction is truly insurmountable when the economic incentive is this massive. Let's just try to put some scale on this, right? Training the largest AI models takes months. It costs hundreds of millions of dollars in compute time and, crucially, power consumption. So if a specialized chip, let's say Google's TPU, can offer even a 5x, maybe 10x improvement in performance per watt compared to a GPU, the cost savings for a company like OpenAI or Anthropic, well, they're measured in the billions over the life of a data center. And specialized chips are already in the market, like I mentioned with Google, and you have Amazon's Inferentia and Trainium lines too. These huge cloud providers, who are the primary buyers of this hardware anyway, they are already providing the software layers needed to manage these specialized environments. So when workloads get massive and specialized, and the cost of running them on general-purpose hardware becomes truly prohibitive, the market will prioritize fixing the hardware bottleneck. Full stop. They'll hire the engineers they need to bridge whatever software gap exists. And this leads us right into defining irreplaceable, doesn't it? Because it really depends entirely on the context. Is the GPU irreplaceable if you define its role broadly? Absolutely. It can handle gaming, science, AI R&D all at once. But my argument is that the definition of high-value AI use is polarizing. It's splitting into two critical massive categories where dedicated efficiency matters most. First, you have training, that months-long huge parallel effort needed to initially build the model. Second, you have inference, the instantaneous deployment and use of that model by potentially billions of users. The millisecond response time. Both of these tasks benefit tremendously from ultra-efficient, dedicated chips. And that makes GPUs, in my view, entirely replaceable in these specific, mission-critical, high-volume contexts.
That's a compelling case for specialization, definitely, especially if we view training and inference as these permanently separate things. But what if the nature of AI workloads itself evolves in a way that actually suits the general-purpose approach better? I mean, Jensen Huang, Nvidia's CEO, he's often talked about his belief that training and inference will eventually sort of merge into one seamless process, models that continuously learn and fine-tune themselves in real time without needing those huge separate retraining cycles. People sometimes call this continuous or blended learning. Now, if the future of AI does involve models constantly adapting on the job like that, the broad, highly programmable architecture of the GPU might actually prove far more adaptable than the rigid, narrowly focused architecture of an ASIC.
A specialized chip is perfect at doing one predefined thing really well. But if the tasks required suddenly shift, they can become obsolete pretty quickly. The GPU's adaptability, its ability to quickly pivot to maybe a blend of learning and application tasks, that could actually guarantee its long-term survival in what's still a very uncertain technological landscape.
I agree that flexibility is the GPU's inherent strength. Yeah, but I think that view relies on a pretty optimistic future state scenario of perfectly fused workloads. Even if models do start to learn continuously, the massive data centers needed to deploy them will still prioritize the most cost-effective hardware for power consumption and cooling. The core math, the parallel computation needed, it remains largely the same, whether it's strictly training or running some kind of refined inference loop. So, if an ASIC delivers, say, 8x better performance per dollar of electricity consumed for doing that math, well, data center operators are going to use it. The rigidity, I think, gets outweighed by the economic necessity of optimizing at the rack level.
Okay, I want to pivot slightly then, away from just the pure technical specs, and talk about market strategy for a second, because I think this reinforces the ecosystem point. You acknowledged Jensen Huang's visionary leadership earlier. Let's connect that directly to the platform's dominance. Nvidia is widely recognized as one of the best-run tech companies globally, with revenues now rivaling giants like Microsoft and Google. This financial power isn't just, for show. It lets them sustain massive R&D investment into the CUDA stack and integrate their hardware and software solutions vertically. Their strategic advantage really lies in their ability to design the silicon, the GPU itself, and then immediately integrate those hardware improvements directly into the established, trusted software platform, CUDA. This rapid, seamless integration, it protects their moat. Specialized competitors, they're often more fragmented, right? They might have great hardware, but then they struggle to build the robust software platform needed to support it effectively, or they end up relying on open source efforts that just don't match CUDA's decades of refinement. Nvidia sells a complete solution, and their leadership structure lets them be incredibly strategic and unified in defending that platform.
That's a strong argument for internal strategic cohesion, definitely. But look, no amount of focused leadership can permanently defy fundamental market forces, especially scarcity and scale. The fact remains that AI adoption is currently far, far outstripping the rate of chip production from any single source, including Nvidia. And that's creating a massive, urgent shortage. So when this scarcity combines with the absolute necessity for efficiency, the market will compel investment into every viable, high-efficiency alternative. We see this most clearly in what the largest cloud providers are doing. Google didn't develop TPUs just to be disruptive. They did it because they needed custom ultra-efficient hardware for their own massive internal AI operations. They realized they couldn't rely solely on general-purpose GPUs to meet their unprecedented scale requirements. And Amazon and Microsoft? They're doing the same now, with Trainium and their own custom chips. These companies, the very customers driving this AI boom, they're creating their own specialized ecosystems precisely because efficiency and mitigating supply risk demand it. That decentralized investment, it's chipping away at the CUDA moat from the top down, I think.
But hold on, even those large cloud providers, they often run a hybrid system, don't they? They still need the flexibility of the GPU for their R&D clients, for smaller startups, and for the huge variety of workloads that don't fit that narrow, massive scale of a foundation model training run. The GPU kind of acts as the universal translator in that cloud environment. So while a cloud provider might invest billions in their fancy fourth-generation TPUs, that chip is essentially worthless to, say, a university researcher running a completely different kind of parallel processing task. The GPU's broad appeal ensures it captures the overwhelming majority of that diverse market segment.
And that brings us right back to the high-value context, doesn't it? If, let's say, 80% of the cost and maybe 90% of the scarcity are concentrated in training and running the largest foundation models, the very tasks that ASICs are perfectly tuned for, then the efficiency argument wins where it matters most, economically speaking. Even if GPUs retain, 50% of the diverse lower compute market share, the high-value, high-demand workloads will migrate to specialized efficiency out of pure necessity. The industry simply cannot afford the power bill or the supply chain risk of relying solely on general-purpose solutions for these specific massive tasks. So yeah, we seem to be at a crossroads. The proven, deeply integrated power of the established software platform versus the necessary raw push for hardware efficiency driven by economic scale. I still maintain that while specialized chips offer impressive metrics and clearly serve specific, high-scale applications, the inertia, the integration, the sheer ease of use afforded by the CUDA ecosystem, that remains the single most powerful deterrent to the kind of complete competitive displacement you're envisioning over the next decade. Disruption, particularly at the developer level, is inherently slow and it's painful. And I'll reiterate that the relentless march toward optimization, well, it has defined the history of computing. The shift from general-purpose CPUs to parallel computing via GPUs, that was driven by computational necessity, not just convenience. The same fundamental force, the economic and computational necessity of achieving ultra-efficiency for these massive, high-value AI tasks will inevitably push the industry towards specialized solutions. Piece by piece, I believe the efficiency gains will just become too vast to ignore, ultimately proving that raw optimization is the long-term winner here.
It is definitely a fascinating complexity trying to forecast these technology roadmaps where, the strength of established software frameworks and the relentless demand for optimized hardware specs are constantly battling for ultimate control.
Indeed, and the listener, well, they'll ultimately have to weigh which force, the profound inertia and developer lock-in of the existing ecosystem, or the unforgiving imperative of efficiency demands and supply constraints will truly prevail in this next really decisive era of AI computing.